Hello and welcome to this video tutorial where I will show you how to use my codes. So for computing the WFT, Windows Fourier transform, and the WT, Wavelet transform. We will start from the Windows Fourier or short-term Fourier transform, which is computed by the function WFTM. You can see that it contains quite sufficient documentation here, while afterwards we will consider also WT, which is very similar, and we will mainly consider only the differences. Let's start from the creating some test signal. Let it be sampled at 20 Hz for 50 seconds. So the times will be like this. And let it consists of one tone at 1 Hz, then another tone at 1.5 Hz, and some frequency modulated component around 3 Hz. Calculate its WFT. Simply pass to the WFT function the signal and its sampling frequency. These are only the two needed arguments generally. So you see it gives you a lot of information about each type of calculation. First it estimates window parameters and determines some optimal frequency bandwidth. We will talk about it later. Then preprocesses the signal, it detrains it by subtracting the third order polynomial field, then filters in the frequency band, applies padding, and then finally calculates the Windows Fourier transform. It calculates for 500 frequencies from 002 to 10 Hz, as you see. If you do not wish to see all this information, you can just set display to off, and then it will not show you anything, or display to notify, which is better. It will show you then if you have some problems, some warnings, and so on. Okay, now let's plot it. What we got. You see, so there are two tones, which are quite interfering here, and one frequency modulated component around 3 Hz. So this is frequency, this is time. You can also see that there are almost no components from 5 to 10 Hz, for example, and usually you do not need to calculate up to the maximal frequency, which is Nyquist frequency, the half of the sampling frequency Fs, and in our case it's 10 Hz. To limit the upper frequency, just use the Fmax property, and for example let's set to 5, and it calculates to 5 Hz. You see? The same can be done with the lower frequency. For example, to see just the frequency modulated component, set it to 2 and calculate from 2 to 5. And you see. Okay, there is also a property of the frequency discretization, which determines for how fine the frequency scale is discretized. It's the property f-step. For example, if you set it to, and it says like optimal frequency bandwidth, this f-step was determined here to be 002, rounded to 0.02 Hz. It's determined usually automatically, but you can set also it manually. For example, set it to 0.1, and you will have quite coarse frequency scale. You see? Yeah. So here it's like one frequency, another's third, and so on. The default is auto, so it determines it automatically for the given wavelet window function and its parameters. It's also equivalent to auto 10, but if you want like it to be determined automatically, but for example twice smaller, set it to auto 20, for example, and you see it previously was 151, now it's 300. slightly more smooth. Yeah, but I would suggest just do not touch it, leave it as auto, it determines it very well and usually sufficient, so just leave it as it is. Okay, let's move on to the more sophisticated properties. Clear screen. Let's close all. Another very important parameter is the resolution parameter, which can be determined by f0. So by default it's unity, and it determines the frequency resolution and time resolution of your window, the trade-off between them. So the higher it is, the closer in frequency components you can resolve, but the worse the time variability is represented. For example, if you set it to 2, you will have, you see, the components, the tones are resolved well, in contrast, but the time variability, frequency modulation is not represented very well. While if you set it, say, to 0.5, you will have the opposite situation, so the frequency variations are well represented, while the tones are completely merged and interfering very much. Okay. There is also a window parameter. So by default it's Gaussian, but you can change it to anything like Hahn, Blackman, exponential, Kaiser A, and so on. Example, determine the window function which you use for the calculation of the WFT. So this is with Hahn function, this is with Gaussian. All functions, all window functions are normalized in such a way that at f0, at the same f0, they have more or less the same frequency resolution. You can also choose your own window function, just specify it in the time and frequency domains. For example, for the Gaussian window at f0, 1, it will be like this. So this is the window function in the frequency domain. Then it's full support, so it's Fourier transform of the window function. It's support in the frequency, so it's from the minus infinity to plus infinity. Then its time domain form, it would be now and its support, full support in the time domain. So you see, the same as this. You can also specify only one of these two to just leave as empty spaces the other ones, and it will calculate it automatically. The same. But it's better, just for estimating of window parameters, it's better to specify both the frequency and time domain forms if known, but if not, then you can specify only one. For example, yeah, if you want like periodic window, not periodic, rectangular, you can specify it like this. ST, and let it be of the 5 seconds of duration, and you will have like this. Not very good with rectangular function. In general, I suggest you to do not bother with this and use Gaussian, which is default, so just do not change it. The Gaussian is, in my opinion, the best, so just leave it as it is. Okay, let's move on. So previously we were plotting in a usual way O over WFT, but you can do this from a function, like just use plot to plot its amplitude do this, and you see the amplitude with frequencies over the x-axis and times over the y-axis. You can also use some plus, which will show you also the time averaged WFT amplitude, or you can use some plus plus, which will also show you the 95% of its evolution in time, its values. You can do the same for the power, which is just pow. It's the squared WFT amplitude. You see? Okay, let's close all and leave. That is most interesting. And here the black lines, they denote the cone of influence, so between them the WFT coefficients, they are determined with a good accuracy in respect to the boundary effects. And you do not observe the boundary effects here because we use by default the predictive padding, which predicts the signal with its values based on its local spectral properties, and thus quite well eliminates the boundary effects. But if you pad it with zeros, you can see they're quite considerable here, and here they become negligible between these two lines. You can also pad the signal on one side with one padding, on the other side with the other padding, by just specifying it in the cell. Also, it's not very useful. Or just like once, for example. Add some your values if you know something. So here it's not very useful. Okay. So the cone of influence, it's determined with some relative accuracy. So they show the range of the times for which WFT coefficients are determined with accuracy rel tol, which is by default 0.001, corresponding to the 1% relative accuracy with respect to the boundary effects. But you can change it, for example, to 0.01, and you see these two lines, they are slightly shifted. So these are determined up to 0.1% relative accuracy. The cone of influence is determined automatically for any window and any its parameters. You can also use the cut edges property, which is by default is off, but you can set it to on, and then it will cut your WFT amplitude to only the cone of influence, and here as well determine its time averaged quantities over the cone of influence. Generally, it's if you need only the time averaged quantities like time averaged WFT amplitude or power, it's better to cut it to the cone of influence and use zero padding, which is most predictable, and then, for example, use non-min, because it sets to nonce ups WFT, for example, amplitude over time, in a second, yeah, and frequencies. So yeah, the same. And in this way you will always know that all your coefficients, all your information which you use for time averaged quantities is fine, and there is no issues, and so on and so on. While if you want to trace all the components and the behavior of the WFT over all times, including near the boundaries, and you are not interested in only time averaged quantities, then just leave cut edges off, and padding is predictive, so just leave the defaults and all will be cool. But of course the predictive padding is not like the ultimate cure, and sometimes there might be some boundary effects and so on, but at least it reduces it much better than the other paddings. Okay. should be also noted that the cone of influence largely depends on the window function and its parameters, like for example on the resolution parameter of the Gaussian window. So at f01 at default it will be like this, you see, and say at f05 it will be much smaller. Okay, there is one more property which can be considered is the signal preprocessing. By default it's on, so it subtracts before calculating WFT, it subtracts the trend by subtracting the third order polynomial fit, and then filters the signal at the frequency bound of interest. Now like from 0, now it's from 0 to 5. Default is on, and I do not recommend to change it, only if you want to experiment maybe, but just to illustrate, for example, let's consider this frequency modulated component, just only in this range where it is. All tones lie below 1 and 7 Hz, but if you turn preprocessing to off, you see there is a tail of the tone which are lying here, somewhere here. That might influence this if this was slightly more to the left in frequency, then they will interfere if you do not bandpass filter. Okay, and finally should be, so just do not touch it, just leave it as default, as on, and do not bother. And finally it should be also noted that you can request a third output, which just gives you all parameters of the simulations, all parameters of the window, which are contained in the WP, and so you can, they will be needed might be needed in the other functions like reconstruction and so on. Okay, let's now move to the WT. The Wavelet transform function is quite the same as WFTM, so it has the same properties, almost all the same properties. There is also a detailed documentation of it, but there are a few differences which we will now consider. So first of all, of course, the Fmin should be higher than 0 for the WT. And you see the cone of influence is also different for the Wavelet transforms that was seen for the windowed Fourier transform. So here it has more conic form because of the logarithmic frequency resolution. And so WT it resolves the components based on their frequency ratio other than difference as was for the WFT, and because of this you have here logarithmic frequency scale. So for example, this is 1, this is 2, this is 4. Okay, by default the minimal frequency for WT is SZ when the cone of influence just decreases to 1 point. So below there are no coefficients determined up to the accuracy, which is by default 1% in respect to the boundary effects. And if you select it below, you will you will be warned that there is no coefficients, that they might, if you had some components here, they might suffer very greatly from the boundary effects in general. Yeah, but this is nothing serious, just warning. Okay, apart from this, there are only two different properties for the WT than they were for the WFT. So the first is f-step, it was for the WFT. Now we have logarithmic frequency resolution and we have the number of voices. So each dyadic interval is discretized on NV frequencies. For example, it's from 1 Hz to 2 Hz and from 2 Hz to 4 Hz there will be the same number of frequencies because it's there on the logarithmic scale, and it will be NV frequencies. For example, 32 here, or you can say put it for 16. You will get more. It is like this is 32, this is 16, but as in the case with the WFT, just leave it as default. It will automatically determine it, and all will be happy. The other different properties, well, before it was window function, now it's of course wavelet function. So by default it's log normal wavelet, but you can set it to morlet, for example. Yeah, let's set it to morlet. You see it's become slightly different, more asymmetric on the logarithmic scale for the morlet. All other parameters, but yeah, but I would suggest just leaving as default log norm. It has very good properties. So the other properties are the same, like F0 you can choose like to be, for example, 2, and you will get like this. The cone of influence will also, if you, for example, from fmin 0, 5 and 0, 1, cone of influence will be like this, and on the 0, 2 will also squeeze a little. Oh yeah, and of course you also can define your own wavelet, just play with it. Usually only the frequency domain form or time domain form is known, so for example for the log normal you can alternatively define it like this. It's at F0 equals to unity, and here is the frequency from 0 to infinity. The time domain form is not known, so we will get the same as previously. Okay, that's quite all. So it should be also noted that if you have like quite big signal with many samples, like this 10,000 samples, and you request to plot it, the plot resultant time frequency representation, WFT or WT, then it will plot not the original returned WT, for example, but its resampled version. It will give you a warning if it is so, just because the resampled version will be reflected in the plot the same as this, because just 10,000 data points cannot be reflected on the resolution with 1080 pixels. So it plots a resampled version, but of course if you investigate in more finer details, like zoom in, then some features might be lost also. This is usually not happens. So if you want to plot without resampling, then just add WR to the end of this, and this will be without resampling. But MATLAB rendering of figures, especially of large figures, large matrices, is quite slow, and on some, if you have many frequencies and many data points, then it might even crash. So it's better to not to plot a usual, because it's some kind of defense from such things. Okay, that's all. So summarizing, you can adjust like fmin, fmax, just to define the range for which you want to calculate the WFT or WT You can also adjust f0, the resolution parameter of the window or wavelet, to adjust the trade-off of frequency and time resolution. Also for wavelet it's slightly more universal than for WFT, and many people for wavelet set it just as 1, for example. And if you want to consider only the time averaged quantities, it's better to use padding 0 and cut edges on to cut the WFT or WT only to the cone of influence, which is determined with good accuracy. All other properties I would recommend to leave as default, so they are well determined automatically or already well established. So that's it. I hope this was useful for you, and good luck, and thank you for watching.